Hey Lou, good evening.
Good evening. How are you?
Good. How are you doing?
Just fine. Already.
Great. We'll just give another minute here, let people come on. All right. Well, we'll go ahead and get started. Thank you, everybody, for coming. This isn't in the slideshow, but a big thank you to everyone who helped out for the RACES deployment for the winter weather. Thank you so much. That was great. Anyway, without further ado, welcome to the February 2026 Austin Amateur Radio Club meeting. Hang on. Do we have any new members or guests?
Yes, hello. I'm a guest. My name's Joseph, call sign KJ5NLA. It's nice for y'all having me.
Oh, hey, thanks for joining us.
Hi, I'm also a guest. I'm Neil's granddaughter, Erica Obert. I'm Kilo Oscar 6, Foxtrot Delta Victor. Thank you.
Erica, you've been here before. I don't think you count as a guest. You've been here before, but welcome nonetheless.
Thank you.
Hello, everybody. I just joined the club online this last month. I am William, and my call is Kilo Charlie 5 Echo India Victor.
Welcome. Anyone else? Do we have any call sign changes or license upgrades? All right, well, nothing heard. Well, to kick things off, the ham of the month for February is Zoe Downing, KN6DQT. A big thank you to Zoe for stepping up, for serving as an officer of the Austin Amateur Radio Club and helping out all over the place with Aries races. It's nice to see new people stepping up and doing stuff. And on that note, if you are interested, do please excuse me. Please let me know or one of the officers know if you'd like to help out. But a big thank you to Zoe. With that, new little segment we like to do, just giving the officers an opportunity to give any updates. Lou, do you have anything you wanted to add or throw in there?
Thank you, Chris. Good evening to everyone. I have one request for simple satellite amateur communication subject. Um, Only thing I've done was very complex, and that's been years ago with tracking antennas, etc. So if someone else has those skills or you know of someone, please contact me and we'll put together a presentation. Any other presentations you want to see, please contact me. I will be doing a complete solar weather in depth in the next few months, but please give me your requests. That's all. Back to you, Chris.
Awesome. Thank you, Lou. Zoe, did you want to throw out anything?
Nope, I don't have anything, but thanks, Chris.
You are very welcome. I think Rex, I don't think Rex is here. He's either has the flu or an alien is about to burst out of his chest. He wasn't sure. Okay, well, my mom thinks I'm funny. All right. Oops. With that, we'll move on to committee updates. Glenn, do you have any updates?
Yeah, hope everybody has thawed out after the ice storm that turned into a sleet storm, which was fantastic. That less freezing rain means less power lines down, which was good for us. Sorry that we canceled Winter Field Day, but all things considered, the place that we were planning on putting it was not a good place for icy roads. So we still plan to do a day where we can test out HF antennas in the field sometime between now and field day. That's still TBD. So look out for that in the future. During that weekend, we had 8 Skywarn nets, which is 8 more than we had all year last year in 2025. So again, thanks to all who sent in the reports that got forwarded to the National Weather Service and were seen by emergency managers in the area. We got a lot of thumbs up from what we passed in. As Chris mentioned at the beginning, Races was on standby to help with shelters. So at a little elevated situation and folks getting ready to deploy. So again, hats off to those folks. The Red Cross did stand up some morning shelters in the area and are now currently shutting those down. And we got to practice our rally plan. So it was a good practice, even though the feared ice did not materialize here. Speaking of Skywarn, there will be the local Skywarn training or weather spotter training on Saturday, February 28th down at St. Edward's University. It's a 2-part sign up, both with the National Weather Service and with the St. Ed's parking crew. We'll send out reminder about how to sign up for that shortly. And then also, finally, yesterday, we finally got the sign up forms ready for the MS 150 for 2026. So a bike ride supporting the National Multiple Sclerosis Society on Saturday, April 25th. Again, the Travis County Aries and the Central Texas Hams will be responsible for the communication between Austin and LaGrange on Saturday. The Houston folks take care of the Houston to LaGrange that Saturday, and then LaGrange to the College Station finish on Sunday. And the last thing that I've got, we'll have a hospital communication drill in the second quarter. If anybody is interested in helping out with hospital communications, please contact Zoe, KN6DQD. Any questions about any of that stuff? Okay, hearing none, back to you, Chris.
Awesome. Thank you, Glenn. Appreciate the updates. Roy, are you around? All right, nothing heard. I can kind of speak a little bit. Nothing, I don't think there's anything major going on with the repeaters. I do know that we are trying to, I don't, Rolf, are you here? Okay. We're still trying to get the Lakeway repeater up, trying to find a good location for that. We are also starting to look to see to get a repeater in East Austin to kind of expand the coverage. And then ultimately, at some point, we want to link all the repeaters together, similar to how they have with N50AK or up in Williamson County with the N5TT system. So yeah. Any questions with the repeater, with regards to the repeater?
I can give you an update on the Lakeway repeater.
Oh, great. Fantastic. Go for it.
We ran into some issues with the hospital, and I think that we've got it straightened out now. It went to their lawyers and everything, and supposedly we've got that information back. I have not heard from them this week. They've actually found a room that we can go into, and it's just a matter of getting the paperwork finished up and the work of running some wire. It's going to be a little farther than we thought it was, but that'll be okay. And we got the money in the bank to do it. So that's where it sits right now.
Oh, fantastic. Thank you so much for the update, Joe. I didn't even see that you were there. Sorry, it's hard to see who's here when you're sharing your screen. Thanks for the update.
Chris?
Yes, sir.
It's Joe Fisher. I have an update here from the Copeland Scholarship Committee, if that's appropriate at this time.
Sure, go for it.
Marie wanted to remind everybody, Marie Vanderweel, who's the longtime chairman of the Copeland Scholarship Committee, wanted to remind everybody of the scholarship, and that the application period for this year is now open, and they should be our application should be due by the 25th of March. And then, and the other thing is to remind people who do apply, you have to apply through the Austin Community Foundation for the Copeland Scholarship, and make sure to review the application tips, because it'll tell prospective applicants, high school seniors, or even those that are renewing, some tips that'll help there. Now, there's one other thing here that see if I can have a look at this. There's two members of the committee that need to be reelected, or reappointed each year. And the committee suggests that the current members, Jimmy Earl, WB5MET, be reelected, and Lori Schmidt, KM5MQ, be reappointed by the club. So if you could carry on with that right here, well, that would be great. Back to you, Chris.
Thanks, sir. Appreciate the update. Yeah, we'll get to. I think there's a note in my thing about the process. we'll have to get kind of scientific about it and not so much. Let me just, I'm trying to adjust my screen here so I can see. Okay, well, actually, let's just dive into that. Any nominations for the scholarship committee, the Copeland Scholarship Committee?
Well, I'm going to assume that my announcement of those two are, in fact, our nominations we put forward.
Yep, sounds good to me.
I'll second.
All right, cool. All right, so we're going to do this super scientific by screenshots, and I'll type it up. But raise your hand if you are within using the Slack raise your hand feature. There we go. If you are to vote for Lori. Raise your hand. I got to take a screenshot. So raise your hand. I'll kind of. Okay, cool. We'll go with that. Fantastic. Cool.
That doesn't count as two hands over here, does it?
No, we're good. You can't vote for your wife. That's not cool. All right. Or maybe it is. I don't know. I think we're okay with favoritism in the club.
If I can say that she is very motivated and willing to be reappointed.
Well, fantastic. Is she there with you or is she elsewhere?
She's in the other room right now. She's getting ready to trundle off to bed. But
okay, well, thank her for her service. Thank you.
You bet.
And then Jimmy Earl. Jimmy? All right. Cool. I will let him know that he was I'll voluntold him. I'll voluntel him that he's up. So cool. All right. Fantastic. All right, moving right along. Oops. Couple club updates. So we've been wrangling around getting the money in a good. Rex would normally give this update, but he is battling what he thinks is a stomach flu. Maybe he drank the water in Mexico. I don't know. But we've gone through the process. We are transferred. For those of you who may or may not know, there are actually two funds that make up, or accounts that make up, the Greenwood Scholarship. They were just, and please forgive me, not a financial person, so I will try to explain this as best I can. They were effectively the IRAs of James Greenwood. So we've gone through the process now to move them to a professional portfolio manager. One of them has been moved over. The other one, we have to sign some more paperwork just because of, I don't know, financial doohickeys, but we will then move those over, combine them so they get the financial power of both of the monies together. And that is happening now. We expect the checks to go out for the scholarship by February 28th. So just a quick update there. Like Lou said, really we could use suggestions for meeting topics or guest speakers, or anything. The club is about y'all. It's not just me, Zoe, Rex, and Lou running the club. So we really want to serve the club as best we can. So please shoot an email, give us a text message, ping us on the radio. Please let us know what y'all would like to see, and we'd be happy to accommodate that as best I can.
Chris?
Yes, sir.
Yeah, this is Neil.
Hey, Neil.
Could you give the club an update on what the Greenwood scholarships amounted to by class this year? Do you know?
I don't know that information off the top of my head. When you say class, what do you mean?
Technician, general, extra.
Oh, I can get that information. Hang on, let me see if I have it. Let me see. Hang on. It's a good question. Hang on. I want to say, okay, so I'm pulling it up, but I want to say most of them were generals. Hang on. Let's see here. Sorry, I'm flipping through my spreadsheets here trying to find it. Please bear with me. Here we go. All right, so and again, this is there are a total of 19 applicants. There are 1, 2, 3, 4, 5, 6 technician license people who have technician licenses. 1, 2, 3, 4, 5, 6, 7, 8, 9 general, and 1, 2, 3 extras. And these scholarship amounts, varying amounts, ranging basically, and we can do I don't know how to release this information, but basically there's folks either got $2,250, $2,250, $4,000, $5,000 was the biggest award. Yeah. Does that answer your question? Neil, you there?
Yes, it did. Thank you.
Okay, cool. Paul, is your hand raised? Did you have a question, or you just raised your hand still stuck up from the voting?
It's just I need to put it down, or
okay.
somebody put it down for me.
No problem. Cool. All right. Oh yeah, we're at the question portion. Any other questions, comments, debates, discussions, anything? All right then. Well, with that in mind, I will turn it over to Lou for his presentation. Hang on, let me stop sharing and let me enable. Share here. All right, Lou, you're now the host. Godspeed. Sorry, was I muted? Did you hear me?
Okay, yeah, do you have,
You're the host now, so.
okay, let me see if I've got are you hearing me?
Yep, I can hear you just fine.
Okay, good. I don't have the audio clip anymore. Okay, well, good evening to the net. This presentation will be on wideband HF antennas. If you'll recall from several months ago, I did a presentation on coaxially driven tuned antennas or resonant antennas in order to minimize the coaxial cable loss. I promised to do a wideband HF antenna presentation that eliminates that limitation and provides significantly better performance over multiple bands. So the objectives tonight will be to introduce wideband HF antenna theory and practice. I will demonstrate that a single horizontal wire antenna can provide both NVIS or near vertical incidence skywave and long range propagation. I'll start out for those that are new discussing NVIS propagation theory. We'll talk a little bit about simplified long range propagation and then how you select the operating frequencies. NVIS, near vertical incidence skywave propagation, is a propagation mode that allows 0 to about 500 miles of propagation without any skip zones. It does require a special antenna and a very careful selection of operating frequencies. So the antenna pattern is basically the old-fashioned cloud warmer, where we want all the energy to go straight up and have a bandwidth of about 100 degrees, and think of holding the filler of a balloon, and it's the shape of the balloon pointed towards the ceiling that we're wanting to achieve. Notice that we'll get about 500 miles range if we're bouncing off the ionosphere F2 layer, which is about 200 miles up. we must operate at or below the critical frequency. And notice that's capital C and capital L. It's a definition in the F2 layer to achieve NBIS propagation.
Hey,
Lou,
Lou.
do you have
Yes.
slides?
What?
Do you have slides?
I thought I asked people
Sorry, we could
if
hear
they
you. We just
were
don't see
seeing
the slides yet. Yep.
my, yes. Oh, I'm sorry. Well, let me start all over. Well, wish somebody had said something. I don't know what's wrong. So, well,
The green share button with the arrow on it.
I can't see anything on my screen.
Oh.
Okay, now I'm back. Let me look at it. I hit the share button, but it's not showing.
It gives you some options to share the thing that you want to share, like either the desktop or
Well, let me
individual.
hit another.
There you
Let
go.
me hit,
There
okay.
you go.
There's a new share button I didn't know about.
Yes,
Okay.
there we go.
Okay, thank you.
And then yeah.
And so let me go up here and start over.
It,
Let me
yeah,
bring up
minimize
my,
that zoom
yeah.
screen and there you go.
Okay.
Back up.
Now, do you see something now?
Yep.
Okay,
Yes, sir.
I'm sorry. I'll just start all over. I
Been
was
there, done
not-
that.
Okay, the objective theory and practice demonstrate that a single horizontal wire antenna can provide both NVIS, near vertical incident skywave, and long range propagation. I will start off introducing NVIS propagation, 0 to 500 miles, and then a simplified long-range propagation theory. And then that'll also include selecting the correct operating frequencies to select these two modes. So, near vertical incident skywave propagation is a mode of propagation that allows 0 to about 500 miles of propagation capability. It's good for tactical and statewide communications. It requires a specific kind of directional antenna, which can be visualized by holding a balloon by the filler cap and down, and its pattern would be headed pointed up in about a plus and minus 50 degree or 100 degree elevation beam width going straight up towards the ceiling. So, in order to achieve this, you must not only have the correct antenna directional pattern, but you also must operate at the critical, slightly below the local critical frequency in the F2 layer. The factors that affects critical frequency, including the time of day, the increased ionization of the F2 layer increases the critical frequency. And of course, during the daytime, the sun is up, ionizing the F2 layer. The time of the year, you would think that the summer would be better, but there's a summer anomaly which heats the F2 layer and causes it to expand during the summer months, reducing the critical frequency slightly. And of course, a big factor is the time of the 11-year sunspot cycle. And we're still near that maximum, which I'll discuss in my solar weather presentation. Other factors that can affect the critical frequency is geomagnetic storms that include coronal mass ejections and coronal holes, which cause ionized materials to impact the Earth's geomagnetic field and upsetting it. And there's, of course, the terrestrial heating, which I've already discussed. Now, NBI's propagation is very critical to the correct frequency selection. If you're off by more than 500 kilohertz, NBIS propagation may not work for you, or at least not at close range. So let's look at the critical frequency versus time. This is the Austin Ionoson in October, but it's pretty much the same as now. The vertical axis is frequency of the ordinary wave from the F2 layer, or the critical frequency, FOF2, in megahertz, and the horizontal is the UTC time, where nightfall is about all around 0100 Zulu, and the sun starts rising around 1200 Zulu. So you can see daytime, sure enough, the critical frequency rises up to about 12 megahertz during the day. Then as the sun starts going down around 0100 Zulu, we're dropping into nightfall, where the critical frequency has dropped down to about 5 megahertz, and then the whole process starts over again the next day. So I discuss the overall ionospheric conditions and propagation forecast on my monthly solar weather presentation, which will follow this presentation. Let's talk about long distance skywave next. This is where a station, it bounces off the ionosphere if we have a reflection point, and then it propagates at a very long distance. It may actually bounce off the earth or the ocean and then continue this bouncing for some, all the way around the world, in fact. So that's the long distance propagation. Successful sine wave propagation path requires that the maximum usable frequency, or MUF, at the reflection location be equal to or exceed the operating frequency. You can see the midpoint in this diagram, and that's the point at which the maximum usable frequency has to be equal to or greater than your transmit frequency. For simple F2 layer to earth bounces, this requirement must be met for each succeeding reflection for a multi-hop circuit. Typically about 1,800 to 3,000, 1,800 miles or 3,000 kilometers. The maximum usable frequency is simply the critical frequency, which we've already discussed, divided by the cosine of the takeoff angle that you can see in the diagram below. So the takeoff angle versus range. It's very difficult to achieve takeoff angles much lower than about 20 degrees. 15 to 20 degrees is the best you can do with simple wire antennas. It takes very complex HF antennas to get down to 10 degrees. So as you can see, with a 20-degree takeoff angle, your first bounce is going to be about 1,000 kilometers out. And I'll show that's about what you can achieve with a simple wire antenna. Okay, frequency versus wavelength. When designing antennas, the length and height in wavelengths determines the antenna characteristics. It is easier to work in wavelengths and then convert to actual dimensions at the designed frequency or frequencies. So of course we know that the wavelength in feet is equal to 983.6 divided by the frequency in megahertz. And I have a convenient lookup table from a military group. You'll see in the left column is some frequency bands or groups that behave about the same, and you can certainly within these bands find the amateur frequencies. The green box in the middle that's labeled long range height is the optimum height in wavelengths or in feet for a half wavelength antenna to operate at the frequency designated. Maximum NVIS heights are shown in the red box, and the minimum NVIS is over to the right, which is really a function of absorption of your radio waves when the antenna gets close to the earth. So let's create a NVIS antenna. Well, we can take a dipole antenna, which has the little generator in it, and we can put a reflector about 0.15 to 0.2 wavelengths behind it. And sure enough, we get something that's sort of like what we want, the kind of pattern we want. We take that same antenna, we use the ground as the reflector, and if we move the antenna up to half a wavelength, we'll get the pattern shown on the left. You can see that it has directionality and it has a low takeoff angle, which is what we need for long-range propagation. If we take exactly the same antenna and we drop that antenna down to 0.25 wavelengths, we'll get the NVIS pattern we want. So how low can you go? Well, it turns out, and this is a 75-meter NVIS dipole, but it could be anything, of course. We want to see what's the optimum height. Well, you can see as you approach about 0.2 to 0.25 feet, which is between 50 and 70 feet, we get an optimum efficient radiating pattern, and the pattern stays omnidirectional if it's a half-wave dipole. So what we want to do is operate somewhere around 0.2 wavelengths to get an optimum NVIS pattern. We can see as we drop down to 10 feet that we absorb a lot of our RF energy gets absorbed and we have lower efficiency. Think of the different colored plots as transmit efficiency. So the basic NVIS antenna rules are: an excellent antenna is a resonant half-wave horizontal dipole at 0.15 to 0.25 wavelengths. So we convert that to frequency for actual operation. Good performance can vary from 0.1 to 0.25. Inverted V is some 2 to 3 dB worse than the dipole, but has a more uniform horizontal pattern, as we'll discuss later. And of course, is easier to implement because you simply have to put up one mast instead of two. And of course, vertical antennas do not generate NVIS patterns. So moving ahead, broadband NVIS antenna design length limitations. Well, it turns out that longer is not better in every case. To operate just below the critical frequency, your antenna needs to operate from 3.8 megahertz to 10 megahertz amateur bands. That is the 75 meter, 60 meter, 40 meter, and maybe 30 meter at 10 megahertz. When the antenna horizontal length, that's the horizontal length, exceeds one wavelength, the horizontal or azimuthal NVIS pattern departs from omnidirectional response and becomes increasingly more directional, even when the correct antenna height is maintained. Well, it turns out that the inverted V actually helps smooth out this asymmetry of the horizontal pattern. Careful selection of proper antenna length and height will allow both NVIS and long-range propagation to occur. So here is an example of the problem. This is a very popular antenna called the Cobra Senior. It is 140 feet long, and you can see colored patterns for different frequencies. Note that its half wavelength is 3.5 megahertz. And it's at 40 feet continuously. So at 2 megahertz, it has almost an omnidirectional horizontal pattern. As we go up in frequency to 10 megahertz, you can see that the horizontal azimuthal pattern becomes more and more asymmetric to the, goodness, as bad as 6 dB difference between the broadside and end-on patterns. So this can be a problem if you're not pointing the antenna at the correct station, even for NVIS propagation. So the secret to selecting a good broadband antenna performance, and this is in general, you want to use very low loss transmission line, 450 ohm ladder line, and I'll show you how to deal with that. Selection of proper antenna length, you want it to be less than one wavelength, and I'll show you some examples. You want to select the effective height, 35 to 40 feet would be optimum. You want to operate at the proper frequencies for range. NVIS, once you get above NVIS, you'll automatically go to long range skip. That's at the half wavelength height. Orientation of the antenna for long range performance, of course, is essential since you want to have the broadside pointed towards the station you want to talk to. And you want to use low loss external antenna tuners and a balun. And I'll discuss why we have to do that farther on. So here is the best antenna for average operation. It's called the Cobra Junior, but there's nothing junior about this antenna. It's 73 feet long and works from 80 to 10 meters. So here is the Cobra Ultralight Junior, 73 feet, which produces a better pattern at the frequencies of interest. It has an 81-foot, 450 ohm ladder line, which its losses at HF frequencies are almost not measurable. You then go to a 4-to-1 balun, or you put your remote auto tuner at this location, and then you put a small piece of coaxial cable. If you're using a balun, you want to put low loss coaxial cable of minimum length to go into your shack, but better to put an auto tuner at this location. So another antenna that you can build that was developed by Army Netcom, Fort Huachuca, Arizona. This was developed by me, but they actually gave the dimensions. So it has two legs that are 33 feet long, and then two legs that are 21 feet long. Those are then connected together and connected to a low loss ladder line. I converted this to build it completely with ladder line, where we simply cut one of the two conductors to a length of 21 feet and let the ladder line support the longer pieces of ladder line support the rest of the antenna. This works quite well. What happens is at higher frequencies, the 21 feet start taking over from the 33 feet, and you have a little bit wider bandwidth antenna in its directionality performance. So let's talk about antenna performance testing. Now, I have a very limited test capability. My HOA limitations at my locations forced me to use my existing Mars horizontal long wire support system. This support system runs between my chimney at 21 feet to an endangered species birdhouse, again at 21 feet, with a total available length of 100 feet. The antenna height, the heading is within 5 degrees of magnetic north-south, which gives me good broadside east-west performance. The height of this test apparatus is not, I repeat, not the optimum deployment height for long range. Best height would be a horizontal antenna from 35 to 40 feet for both NVIS and long range performance. So this is my test antenna strung up. You could see it going from my chimney, where there's an auto tuner, to the endangered species house behind me. I ran the ladder line propped up on a tree, and then to a support where I had the balun, and then I had coaxial cable about 50 feet of low loss coax going into my tuner. But I also mounted auto tuners on this sawhorse for testing of remote tuners. So the block diagram of the test apparatus included an ICOM 7610 transmitter, a 500 watt Tokyo high power amplifier that is not used during tuning, a digital vector RF watt meter, the tuner, either an LG AT 5000, 1000, or two other tuners, remote tuner, with 50 feet of transmission line. That's a balanced open line going to one of two test antennas. Actually, 4 antennas were tested total. Once the tuner had found a solution, I would then bring up the amplifier to full power to make sure the tuner and everything else was working. So I ran some communications NVIS tests using the Cobra Ultralight Junior. This was at 8 December, 0100, 7 p.m. net. on 5.2 megahertz, and so the critical frequency was about 6 megahertz. I ran 350 watts, and I was sending a digital information to a station, Alpha Alpha Romeo 6 Sierra Mike, in Louisiana, central Louisiana, and I did a radio check, and I was loud and clear, and he was loud and clear to me. I was able to send and receive additional 5 digital messages from Louisiana stations and from Texas stations. The model gain at 5.2 megahertz for this Cobra Ultralight Junior was 3.42 dBi. And here is its Cobra Junior NVIS pattern at 5.2 megahertz. Had I put this at 30 feet, it would have been about a dB and a half better, but that's the best height I could get, but it also worked very well. The digital modes that we have to run in Mars require a good and readable to a loud and clear signal because they're very poor quality. So being able to get digital message traffic through to Louisiana demonstrates how well this antenna works. I then used the Netcom 6644 450 ohm ladder line antenna at 6.9 megahertz, which is with a critical frequency of 7 megahertz. Again, I was running 350 watts. I was net control, and I was able to talk loud and clear to Houston and to Fort Worth. I also received traffic from Texas and Louisiana stations. The modeled gain was 5.14 dB, a couple of dB better than the 60-meter antenna. And here is its directionality, as you could see, still a good in pattern, a little bit of asymmetry, but that's what the ladder line antenna, or the Netcom 6644, helps us with. It reduces the asymmetry some. So additional antennas tested and are the Netcom 6644 with 300 ohm ladder line, and I'll give you a little bit of detail on that. It's a ruggedized implementation for military operations, and maybe for you if you want a ruggedized antenna. And then interestingly, Netcom has suggested building the same antenna using a number 18 lamp card or zip card. It makes a field expedient antenna and can be constructed with Home Depot materials only. And it was able to talk clear to Houston, to Louisiana and other stations using 350 watts. So it works surprisingly well. So the assembly of the 6644 300 ohm antenna is shown. I'm using a DX Engineering material that allows the antenna to be strain relieved, the 300 ohm line to be strain relieved, and then the dipole constructed using, again, the same technique with the one leg 21 feet and the other leg 33 feet on each side. I then went ahead and built up the lamp card antenna using the same material. And it worked just fine. I did use a 4-to-1 balun, which is probably not available at Home Depot, but we actually have done this with the Texas Military Forces commo team, and they didn't use the balun, and it still worked quite well. Here is the PVC alternate T and N insulators made with PVC half-inch PVC pipe fittings with 9/32 diameter holes drilled. So you can build this antenna completely with materials from Home Depot. So let's talk about what happens at the long-range EasyNet modeling, since I couldn't actually measure that. And you'll see how the antenna switches from NVIS to directional. It turns out that at both the Cobra and the 6644 Netcom antennas behave very similarly at 10.1 megahertz. You can see the antenna switching from the patterns I showed earlier to directional capability. This again is a height of 40 feet. And the gains are 7.1 dBi, which is very respectable. And the takeoff angle in this case was 35 degrees. So it's not going to be super long range, but it's going to do pretty well. Here is the current distribution in the wire. So it's almost a wavelength long. At 14.2 megahertz, 20 meters. The takeoff angle is now 25 degrees, the elevation angle 25 degrees, and you can see it has a very mature low takeoff angle antenna with good directionality as seen in the horizontal azimuthal pattern. You would have to point the broadside directly at the station you wish to talk to at long range for this to be effective. But now the same antenna that was in VIS has good directionality at 20 meters. All you did was change the frequency, maintaining a height of 35 to 40 feet. Current distribution. Now the Cobra and the Netcom antennas differ in their performance because the extra wire in the Netcom 6644 takes over and helps out a little bit. So here is a takeoff angle of 20 degrees. Here's your 20 degrees antenna at 18 megahertz, an amateur frequency. And again, a very nice beam width, 27-degree beam width. This antenna would perform well in spite of the losing some energy going straight up. And the Cobra current distribution is shown. The Netcom antenna has a little bit more gain, 10.22 dB. The beam width is a little bit wider because that smaller wire is starting to take over. It has the same 20-degree takeoff angle, so that smaller, shorter pair of wires is starting to help out a little bit more and getting the gain higher and maintaining a little bit higher, wider bandwidth, horizontal bandwidth. You can see the two wires absorbing energy at different wavelengths and different components of wire. So the problem is once we got both of these antennas over 20, we went to the 21 megahertz from 18, both antennas just fell apart. They ended up with a crow's foot performance as seen with the right horizontal component, horizontal azimuthal antenna pattern on the right. It does have a good low takeoff angle of 15 degrees, but the gain is 8 dB, but notice it's going to be at 4 different angles, so I'm not sure what that really means. You'd have to point the antenna a little differently to make it work. Maybe for just general amateur operations, you would be able to do that and just talk to whoever you wished. And the current distribution gets complicated. The Netcom antenna has the same issue, and you can see the current distribution on the antenna. It's too long, and that's causing all sorts of problems. So this antenna is good to 18 megahertz. You can go from long range to NVIS by simply changing the frequency and maintaining a height between 35 and 40 feet. So antenna tuning. Broadband HF antennas will have wildly varying impedances that cannot be resolved to a low SWR solution with the internal tuners found on modern HF rigs. The rig will simply shut down if the SWR is greater than 3 to 1, and that's to prevent arcing over inside the tuner, which at very high SWRs requiring very high voltages. A wide range external tuner must be employed to lower SWRs to less than 2 to 1 so that the rig will deliver full power to the antenna. That's the caveat to running wideband antennas, but that's what Mars does all the time. So you have two different options. You can either locate your tuner at your rig, or you could locate the tuner at the antenna. The tuner located at the antenna is the preferred method for marine, shipboard, and military HF antenna systems. Here's an example of a typical military Army Mars military antenna system. There's an HF PRC 150 transceiver. It puts out 20 watts. It's driving a 125 watt or a 250 watt amplifier. And then there's cables that go to the remote located auto tuner that then tunes the antenna. So how do you implement that as an amateur radio operator? Well, the best auto tuners, remote auto tuners, are no longer available. They were sold by SGC and MFJ, both companies which have gone out of business. So my recommendation is one of two different remote tuners. The Chameleon, CHAURT1, or the CG Antenna Limited, the CG3000. Both of these are available from DX Engineering and other vendors. Let's go into a little bit more detail. The Chameleon URT1, very good little tuner. It has built-in bias Ts, and we'll talk about what bias Ts are all about in a moment, but they basically allow you to power the auto tuner, which is a microprocessor-controlled machine, remotely, providing DC power and RF through a single cable. So the URT1 requires that you tune at 0.5 to 15 watts. Then you can crank the power up to 100 watts and everything is cool and it's doing very well. It has a metal case that has O-rings on everything. It's very watertight, very nice constructed. But you have to be very careful about tuning it at low power. The CG Antenna Limited is a very interesting plastic cased auto tuner. It uses, instead of LCCL, it actually realizes the tuning in a pi network, which is LCL, much superior to the way that MFJ did its tuners. This is a Chinese-built product. I own one, have tested it extensively, works very nicely, and you can tune it at 100 watts. So the advantage to this is that, as you can see in the diagram, your transceiver drives a bias T, which mixes the DC and RF. You can have a very long coaxial cable, 600 plus feet. It then goes through a choke balun, maybe, to a bias T that separates the power into DC and RF. The DC powers the auto tuner, and the RF goes to the auto tuner that then matches to the antenna. This is a very convenient process if you have long distances to run, where your tuner is, where your antenna is significantly distant from your radio. So this works very well. Here is the VSWR test results with my antenna at 21 feet. This is the CG Antenna Limited CG3000. Note that once we get to 4 megahertz, the other frequencies are very low and the antenna is not very efficient, but at 4 megahertz all the way to 14 megahertz, including some basic Mars frequencies, the auto tuner found an excellent VSWR for both the ladder line Netcom antenna and the Cobra antenna. So very, very low SWRs. Pi network worked very well. And I got a similar performance from the URT1. It performed surprisingly well. I'm sure it has higher losses because it has smaller inductors and it's a metal housing, but it actually performed and found low SWRs over these same ranges without any problem. So excellent tuner also. You just must be careful to tune it at low power. So bias T availability problem. Well, if you want to put a remote antenna the HF auto tuner, it is convenient to send, of course, both RF and DC power through a single coaxial cable using bias Ts at each end of the transmission line. A lot of people are actually using RG8X because it's 50 ohms. As long as you maintain a 50 ohm transmission line and the tuner is remote, you're going to have low transmission line losses. The two available bias Ts shown below, the one on the left is the SGC bias T, and the one on the right is the MFJ bias T. Both are no longer available. So I did a search, a design, and ended up designing and building my own bias T. I call this the W5IFQ bias T. I have made a limited production run on this. I was able to find a bias T circuit board, again, a Chinese device, but I tested this all the way to 500 watts at 1 to 2 amps. It's very good product. I've not been able to break it. So I can send you a design and construction instructions if you wish. About $50 worth of parts, or I will build one for you for quite a little bit more than that based upon my labor. So we have a solution to solve the bias T issue. So bias Ts, again, can be used to send both DC power and RF to the remote tuner through a single coaxial cable. Very convenient, allows you to use only one cable. Lightning and EMP mitigation must be implemented to protect your tuner. If the antenna hits lightning hits your antenna, it's going to damage the tuner unless you have some way to disconnect the auto tuner from the antenna during a lightning event. I have a solution to that. Please contact me. Further, plastic cased tuners like the CG3000 must be protected from solar ultraviolet rays. The sun the sun in Texas destroys plastic housings. But if you just put a shade over it, the CG3000 is completely watertight as long as you tape up the connectors. And so as long as you give it some shade protection, it's just fine. Again, contact me for design details. I have a lot of experience. So tuner at the rig. Well, this is where you put a 4-to-1 balun. You run your ladder line as far as you can, as close to your station window or entry point for your rig. You put a 4-to-1 balun, and then you run a very short, low-loss coaxial cable like RG8 or LMR 400 from the 4-to-1 balun to your tuner to your transceiver. I ran tests with the LDG AT 1000 Pro 2 and found that unlike the earlier LDG tuners, it was able to find solutions on all of the antennas that I just discussed. And here is the two Cobra Junior and the Netcom 6644, clear down to 2.2 megahertz. Height of the antenna was 21 feet, and you can see the tuner found good SWR location, good SWRs from 3.3 megahertz all the way to 14.48 megahertz. So that's a good tuner. It's actually cheaper than the CG3000 to purchase. So a very good product. So conclusions. An NVIS antenna must maximize elevation gain vertically. This is accomplished by operating at a vertical height of 0.25 wavelengths. NVIS operating frequencies must be slightly below local critical frequencies of 75 meters, 60 meters, or 40 meters. That is 3.8, 5.3, and 7.2 megahertz. As the same dipole height exceeds 0.5 wavelengths, again, you're changing the frequency, so its height is going to go up. You didn't change anything but the frequency. The horizontal azimuthal shift to long-range characteristics. This will automatically occur as the operating frequency is moved up to long-range frequencies of 30 meters, 20 meters, and 17 meters. These antennas did not work well at 21 megahertz, but I'm sure we could figure out how to make that work. The overall length of the dipole should not exceed one wavelength to minimize horizontal azimuthal variation. Additional modeling shows that heights of 30 to 40 feet horizontal are good and easily achieved with available telescoping masts. External tuners must be used to tune the antenna to 50 ohm to maximize RF power transfer from the radio to the antenna. Any questions? Hopefully, Chris will be posting this on the website. A PDF will be posted. I provided that to him. Please contact me if you have any questions. But this lets you have a single antenna. If you get it between 30 and 40 feet, you can operate up to 18 megahertz long range and NVIS down to 75 meters. Questions?
Well, I've got a
Nothing.
little
Go ahead.
Yes, Joe Fisher. I've got a little comment or question, I guess. You said one of the antenna tuners had a Pi network in it. Is that
Yes.
the only one?
Yes. Well, it turns out that the SGC series would try the LC and the CL realizations, and then if those didn't work, it would then switch to a limited Pi network.
Interesting.
Yeah, but it turns out that the CG3000 does a Pi network all the time. I
Yeah.
opened it up and snooped around, and other references said that was the case. You get an extra pole in that Pi network, and the component values are actually smaller. So you get a wider range tuning capability by going to a Pi network if you're smart enough to be able to implement it. And apparently the Chinese figured that out. Very good product.
Yeah, well, notice that if your series components have a low enough reactance at the operating frequency, you default back to an L network anyway. So yeah, I could see what they're trying to do there. Yeah. Very good.
Very smart, good design. Any other questions?
Yes, Lou, in a
Nothing.
previous conversation,
Yes.
you got me in a previous presentation. I think you talked about putting a lightning arrestor, near at a ground rod where you would bring an antenna line down to it and then bring that back into the shack. How does that apply in this situation?
Well, you want to have a lightning arrestor in your coaxial cable that enters the shack. You can put a lightning arrestor on the remote auto tuner, but it turns out that that's not going to save the auto tuner. What I do is I have a 5,000 volt 30 amp hydro from the antenna when it's not in use. So I use the power that is being supplied to the auto tuner to activate a single pole double throw relay that simply disconnects the antenna when it's not in use. I've been doing that for the last 30 years at this location. Before then, I was regularly losing SGC auto tuners to a lightning strike somewhere in my neighborhood and knocking out the very sensitive diodes on the SWR measuring circuitry on the circuit board. That has completely ended by going to a relay. I can provide that kind of information. The relays are about $100 each, but they're very rugged and long lasting. So that's the best way to protect the auto tuner from damage.
Lou,
But yes.
One of the things you have to notice, because I just studied up on this a little bit a month or so ago. The surge protectors that are available, and there's some new ones coming out. but they don't all pass DC for whatever reason. I mean, you would think that they probably would. But of course, in that case, you've got to put the bias T ahead of it, or you'll never get any power up to the tuner.
Yeah,
But
well,
after the
there's
kid-
two different two different types of uh, lightning array block. They both have advantages, but you could certainly find a good lightning register that passes DC. And so again, contact me and I'll give you the model numbers for those. But yeah, but you're right. I've had several Mars members who couldn't get the auto tuner I'd built for them to work. And when I asked them what their lightning register device was, it was a DC block. And so we just swapped that out and that fixed the problem. Any further questions? Okay, I'm going to unshare and then bring up my solar weather. Well, okay, share. Okay, is everybody seeing my slide?
Yes, I see
You
it.
bet.
Oh, okay, good. Okay. Solar weather, 3 February 2025. Please notice the aurora borealis in Birmingham, New York. So we have some serious issues with a coronal mass ejection on the 20th of January. So, well, now it's not changing. Okay, now it is okay. So, solar cycle 25 progress. Again, we're seeing the smooth predicted sunspot number starting to drift down a little bit. The predicted solar flux index is drifting down a little, but we're still have a very high solar flux index. So things are still looking very good. Notice that the solar flux index is 174. It can be as low as 50 at the bottom of a sunspot cycle. Our 3-day geomagnetic forecast is very quiet conditions February 3rd and 4th. On the February 5th, we may have a glancing blow from a small coronal mass ejection. That's again, NOAA is not sure that's going to happen. Now, we have had a serious flare event. Sunspot 4366 has been throwing X and M flares. And in fact, while we've been sitting here in the last hour, it's thrown 3 M flares, including a Mach 1.29. And it is slowly moving into a geo-effective position pointed directly at the Earth. You can see the picture here. But notice there's even been an X 8.1. That's a serious flare. So very active sunspot region, throwing a lot of flares. Make sure you have your tinfoil hats on, high. So even in visible light, you can see 4366. Notice that we have 3 beta sunspots, 3 alpha, and then we have 4366 beta gamma delta, and NOAA considers it still growing. very serious sunspot. The flare probability seen in the lower right-hand corner of this slide, 80% for M flares, 40% for X flares. There's even a 50% for proton flare, proton emissions. And I'll show you in more detail, but if you look at the solar flare class, anything that's yellow is a blackout, is a solar blackout if it's directly overhead. So there's just one flare after another almost continuously. It's only a matter of time before one of these produces a serious coronal mass ejection, and we just need to continue to watch for that. So this is anytime you see multiple changes in color that are close together, that means that the magnetic polarity of the sunspot is very close together, and a magnetic polarity difference is what causes a magnetic flare, which is what a sunspot flare is. It's just a shorting out of two magnetic fields that are of opposite polarity. So a very serious, busy sunspot, and it's going to be moving right, which means it's moving into more geoeffective position pointed at the Earth. Here's X-ray flux from 1 to 3 February. You can see the radio blackout threshold that I've put on at 10 to the minus 5th watts per square meter. And it's spending an awful lot of time above that red line. If that is overhead and not somewhere else on the Earth, that's going to produce, it's going to ionize the D layer where you are, and your radio wave is not going to make it to the F2 layer. At 1412 Zulu today, during our Mars net at 7.5 megahertz, this occurred. The signals on our net were reduced about 50%, but this wasn't right on top of us. Had it been over, a little bit later, it would have caused us serious consequences. Fortunately, the sun wasn't quite on top of us yet. The attenuation at the center of the yellow area can be seen in the bar graph on the right. And the 1 over frequency squared inverse square of the frequency can be seen in the shape of the red curve as frequencies. And so 5 to 10 dB of attenuation, where 3 dB is half power, would be a serious attenuation of your signals. Earth's geomagnetic field, this comes from 13 mid-latitude located geomagnetic observatories all over the Earth. And it's an average of all of those 13, and it's very quiet. 2 to 3 planetary K-index numbers. So quiet at the moment, and no problem until we get to some kind of a coronal mass ejection impact. Geomagnetic conditions, 3 February, the Bravo Zulu, which is the interplanetary magnetic field polarity, is negative at a minus 2.99. So the material from the sun can interact with the Earth's geomagnetic field and cause a reduction in its strength, but not too bad. Speed is a little bit below the normal 350 kilometers per second, and density is typically 1 to 10 protons per cubic centimeter, so that's well within limits. Disturbance storm time is the polarity of the horizontal ring field, equatorial ring field, and its polarity and intensity is a good measure of the intensity of a geomagnetic storm. If you look down in the bottom, you'll see the disturbance storm time in January, and you can see the DST drop to greater than minus 200 during the coronal mass ejection event that I will show you at the end of this presentation. So this is a good measure of of the intensity of geomagnetic storms. The ghost magnetometer is got some fluctuation in it, and it's a measure of the Earth's geomagnetic field. It's equivalent to the planetary K index from the terrestrially located geomagnetic observatories around the Earth. Coronal holes are simply a weakness in the sun's magnetic field that allows higher than normal solar wind, which is a completely ionized material, to leave and hit the Earth. We have no coronal holes that are facing the Earth at the moment, so this is a non-problem. Just for those that don't know how the ionosphere is created, let's take that for just a moment. The ionosphere is created by a combination of gravity and solar radiation. As a gravitational field is reduced as you go up in altitude, the atmosphere gets thinner and thinner. When we get to the height of about 300 to 350 kilometers, the atmosphere is so thin that the monoatomic oxygen that is disassociated by solar radiation or ionized by solar radiation cannot recombine in any reasonable amount of time. That's why we have an F2 layer at night. So it's very thin up there. How thin is it? Well, if you look to the left, you'll see that the International Space Station orbits only 50 kilometers above where our F2 layer reflects your radio waves. As you go during the daylight hours, as you go down in altitude, you end up with the F1 layer and then the E layer. The F1 layer is extreme ultraviolet radiation and ultraviolet radiation. The E layer is produced during the daytime hours by the extreme ultraviolet and soft X-rays, and then we get down to the D layer, which is up to no good. It doesn't reflect radio waves. It just absorbs your radio waves on the way to and from the F2 layer, and it's produced by Lyman alpha radiation and hard X-rays. It fortunately stops X-rays from injuring human beings on the surface of the Earth. And so it's a very important layer. As soon as the sun goes down, the D layer completely disappears. And so there's no D layer at night, and that's why low frequency propagation on 80 meters and 160 meters does work. So, Austin ionoson status. Well, it turns out the Austin ionoson is working again and is now sending data to GURO. But it's still scheduled to shut down, but I cannot get any date from Applied Research Labs on that, and I used to work there, so I don't know. I recommend that all users move to the Eglin Air Force Base ionoson EG931 just in case. Gabbit I've already shown you this once, but for the Eglin ionoson today, the critical frequency is shown on the left in megahertz, and you'll see that its behavior, universal time, UTC time, it's getting up to about 9.5 megahertz, maybe 10, and then it's dropping down to 4 megahertz at night. And then as soon as the sun comes back up, it starts to rise back up. Notice that the critical frequency varies dramatically during the sunrise and sunset portions, so that you must adjust your frequency if you want to maintain NVIS propagation. Our net controls for Mars have to do this very carefully, and if they don't, suddenly all the close-in stations disappear. So it's very important to do that. Here is the Gabbit for the Austin ionoson, and as you can see, it's working well. The square at the high model, but it looks at ionoson data to do the scaling. confirm that the model is working, blue squares. If you want an actual ionogram, you can use DID base and go to the station list, either select Eglin Air Force Base or Austin Ionoson, and then simply go to, year, month, day, hour, and you can see the actual ionogram as shown here. Here's the Eglin Ionoson ionogram for 1 moment, 11:47 Central Standard Time. And you can see that it's about 10.2, 10.3, 10.3 megahertz. And all the ensuing parameters are shown in the table on the left, including the MUF table on the lower left-hand corner. D is the skip distance in kilometers. And the MUF is that critical frequency that would work. So notice that at 3,000 kilometers, the critical frequency is 34.3 megahertz, which means 10 meters is open. Time shifting, Eglin Air Force Ionoson is east of Austin at about the same latitude. So sun angle is about the same. So the same radiation from the sun. What happens to the ionosphere over Eglin will occur over Austin about 45 minutes later. So this is a simple longitude difference converted to time. So a look at Eglin FOFT 45 minutes earlier to see what is going to happen over Austin. Remember, the most rapid change in FOF2 occurs as the sun is rising and setting, morning and evening. Take that into account. Okay, notable solar weather events in January. On the January the 18th, we had a X flare, an X 1.9 long duration solar flare was observed around AR 4341. This was associated with a type 2 radio emission and other information that told us this was a coronal mass ejection event. You can see the flare in the lower left-hand corner. It took a couple of days for the coronal mass ejection to hit the Earth's geomagnetic field. You can see in the ghost magnetometer the impact of the coronal mass ejection on our magnetic field, a very big impact. You can see the effect of the effect to the planetary K index of all the mid-latitude terrestrially located magnetic observatories. And then finally, this is the effects of the coronal mass ejection on the ionosphere. The Aurora Borealis was seen in central and northern United States. And interestingly, this coronal mass, the flare produced a proton event, which doesn't happen too often. These are protons that come from the flare. And it take about 8 hours to get here. They travel at almost the speed of light, and they're real particles. They're protons. They have mass. When they hit the Earth's geomagnetic field, since they are charged, they spiral around the Earth's magnetic field and dump into the Arctic, producing very, very high D-layer absorption in the Arctic. And you can see the effects. Notice that mid-latitudes, we would be in good shape. We ran Mars nets that causes no problems unless you want to go over the poles, propagation-wise. Probably not a good idea to fly over the poles in an airliner multiple times because you would be irradiated by protons. But you could see the amount of attenuation in the poles. So a very interesting flare mass ejection complete with a proton event. Very interesting. So solar weather data is available on the Region 6 Army Mars website. Click on menu, select solar weather. You'll have the Gabit, the Eglin Gabit is automatically shown, but you can use Gabit to go to the Austin Ionoson or any other Ionoson in the world. You can also select for Ionosons. I recommend Solon Ham website. And this is an excellent site supported by a Canadian station. He draws together all the information that's important for solar weather. Excellent site. I can't speak well enough for him. This is how I get most of my information. One of his new banners is the real-time solar wind that gives you the speed, the density, Bravo Zulu and Bravo Tango. The first three are very important for our propagation capabilities. Also, we have good old spaceweather.com has the same information, but it has some great Aurora Borealis pictures and other nice facts that the other websites. Questions about solar weather? Again, the solar weather is very important if you're an HF operator. You need to know what's going on because it's like operating a sailboat. If you don't know what the wind's doing and the tides are doing, you're not going to go anywhere. If you want to communicate with a specific person or a certain area, you need to know what the solar weather is going to do to you. Questions? No questions heard. Back to you, Chris.
Awesome. Thank you, as always, Lou. Before we wrap up, anyone got anything else? Well, cool. Well, thank you all. Thank you all very much. Feel free to join us on Saturdays for breakfast at Waterloo on Burnett. Have a good evening.
Good evening.
73.
73s.